In this video, I'd like to talk about evaluating logarithms. And these types of problems can be a little bit confusing because of the notation. The notation here is a bit awkward, and it takes a while to get used to it. But essentially, what we're trying to do is find a missing exponent. So let's start with this example problem. And for starters, you want to figure out a way to just say this. And the typical way that people say this is that it's log base 2 of 8. So our base is 2, and we'll say of 8. And what this means, if we write this in exponential notation, essentially we have an exponential expression with a base of 2, and let's say this is equal to x, where we're missing the exponent x. We don't know what that is, but we know that this will be equal to 8. So when you have log base 2 of 8, the exponential expression equivalent to this is 2 to that missing exponent, 2 to the x power, is equal to 8. So when you see these, you want to think 2 to what power gives you 8? And you can think this through. That would just be 3 in this case. So the logarithm, log base 2 of 8, is equal to 3 here. And that should make sense because if you plug in 3 for your exponent, 2 to the third is equal to 8, since 2 times 2 times 2 does equal 8. So in practice, they're often not difficult to evaluate, but getting used to the notation and getting used to rewriting this in its exponential form can be challenging. But the way you want to remember it is that the base is always the base of the exponential expression. The logarithm is an exponent. So if you can remember that logarithms are exponents, then that's the missing variable, the thing we're trying to find here. And then whatever is inside the logarithm is what your exponential expression is equal to. So let's go through several examples since, like I mentioned, this can be a little bit confusing. So this one we would say log base 4 of 64. And we're trying to figure out what this is equal to. And let's say it's equal to y in this case. So we can rewrite it as an exponential expression. This is 4 to what power gives you 64. And that missing exponent we're going to call y. So our base of the exponential expression is 4. And that exponent for this exponential expression, that's equal to the logarithm. That's y. So 4 to some power y gives you 64. So we need to figure out what exponent can we put here so that this equation is true. And in this case, y would be 3, since 4 to the third power, which is 4 times 4 times 4, that would equal 64. 4 times 4 is 16. 16 times 4 is 64. So in our box here, this logarithm would just be equal to 3. But again, just remember that logarithms are the exponents, or in this case, they're the missing exponent that we have to find. So let's keep going. We'll do this other one right here. This is log base 9 of 9. And you don't have to write the exponential expression every time, but it's a good habit, especially when you're first learning these, because a lot of more advanced problems, you want to be comfortable going from logarithmic notation to exponential notation. So this one, I'll say the logarithm's equal to z. And we have the base of the exponential expression is 9, and that exponent we're going to raise it to is z here. And this will be equal to whatever is on the inside of our logarithm, which is 9 in this case. So this question is just asking 9 to what power gives you 9? And in this case, we just want to multiply 9 once so that we get 9. Or in other words, z is equal to 1 here, since it's true that 9 to the first power is 9. Anything to the first power is equal to itself. So in this case, we would put in the box that z is equal to 1. And we'll do several more of these, since these are more from the introduction exercise, and The next several problems will all be from the more advanced exercise, but they all follow the same pattern. You want to rewrite it in exponential expression. So this is log base 10 of 10,000. So 10 to what power would give you 10,000? So 10 to some power, we'll call it a, equals 10,000. And if you multiply 10, there are 4 zeros here. If you multiply 10 4 times, then that would be 10,000. So that missing exponent that we're looking for, which we called a, that's just equal to 4 in this case. Since 10 times 10 times 10 times 10, if we multiply 10 4 times, we would get 10,000. And in general, 10 to whatever power essentially just tells you how many zeros you would add after the 1.